Thank you. So I know we have an hour and a half. Just
More like an hour.
we have an hour. Oh, you told me an hour and a half. Well, good thing I didn't plan for an hour and a half. Well, how long do we have?
We have the room for an hour and a half, but I think a lot of people will end up.
Yeah. Well, so what I was going to say is that if you're going to leave at 1 o'clock, please raise your hand so I can have a sense of how many people have to leave. Okay. Good. So basically, I'm with the Naval Postgraduate School now, and I was here before, and it's always a great honor to come here and speak. I love this place, and I love the people. But let me tell you a little bit about what I'm doing now. NPS is the Navy's research university. This is the coast of California, and NPS is there in Monterey. But I don't live in Monterey anymore. 2.5 years ago, I moved to Arlington, Virginia. This is the Virginia Tech Research Center. And that is my office, and NPS has this collaborative relationship with Virginia Tech. And who knows what tomorrow will hold. But right now we have a collaborative relationship. We might be moving to a Navy facility nearby. In this region of Ballston, Virginia, you have the National Science Foundation and DARPA and Office for Naval Research, and those are all within a 4-block walk of where I am. But Navy's building a building as well. So we are hiring. So if you know of anybody who's looking for a position after graduation, or anybody who wants to work on a PhD or anything like that, please call me. My problem is that I have more money than people. I just cannot hire enough people who can do this work. And this work is really, really hard because it covers the entire scale of the computer stack, from tiny bits to complete cloud computing systems. Now my group, we named it a few years ago, we're the Deep Group. We do evaluation, trusted computing. We do exploitation, like cell phones and documents and hard drives. And we work very closely with other parts of the US government, with law enforcement, DHS, and we also work with foreign governments. So I was just in Mexico at their Science and Technology Center for the Mexican Federal Police, and I visit the Metropolitan Police in London, and I'm going out to Zurich in a few months. So it's a tremendous amount of fun, but it's just too much work. Now, digital forensics has been around for a while, and it used to be what digital forensics was largely used for was establishing possession of contraband information, like child pornography, stolen documents, hacker tools. And one of the key things you had to do is not just show that the data was there, but to show why it was there. So a few years ago when I was buying hard drives here, one of the hard drives that I bought had evidence of previous presence of child pornography on it. But it didn't actually have the child pornography on it anymore. And I called up the FBI, and they said, oh, do you actually have it? And I said, no. And they said, well, then we're not interested, because I couldn't show a clear chain of custody. Now, I started this work back in 1995 when I was running an internet service provider. Back then, we didn't call it digital forensics. We just called it computer security. We were trying to figure out what was going on. And that up there, that's a little graph of the input and the output network load at my ISP during an attack. And the little green is where they uploaded a copy of Windows 95 a few weeks before it was publicly released. And then the blue is where everybody else is downloading it from our server. We got wares. And then in 1998, I started a company called Sandstorm Enterprises. And we now know that what Sandstorm was doing was selling computer forensics tools. We thought we were selling computer security audit tools. It didn't work out very well for me. I didn't get rich. And there's a reason that I didn't get rich that I now understand, which I'll talk about in a few minutes. But remember that people who make computer forensic tools don't get rich. And then this is a picture of my lab here at Harvard, which is actually 110. It doesn't look like this anymore, but I think the shelves are still there. They were installed for me so that I could put my hard drives on the shelves. And what we started doing was back in 1998, a bunch of the computers that I bought for the phone scanner had previously been used by law firms and a medical center. And we said, well, all this confidential stuff. So we actually started buying used hard drives for their data and then developing ways for automatically finding the good stuff. Now, my goal these days is to use computer forensics for investigations. We do data extraction. We then try to put it all together with data fusion. We try to correlate from multiple machines. We can automatically identify networks, human networks, computer networks. Much of the research that I'm doing falls into what's called triage, which I've learned is a technical term. It means prioritizing work based on the content rather than based on outside factors, like whose work it is. And in my research, there are three underlying principles. The first is that automation is essential. Most computer forensics analysis these days is done manually. We have tools that allow the data to be visualized, to do search, but it's really up to an analyst to put it all together. I'm trying to develop techniques that can do this automatically. The second thing is to concentrate on the invisible. It's easy to wipe a computer. For example, if your computer has a little hard drive in it, it's a laptop, just hit it with a hammer, it will shatter, and nobody will ever be able to get the data off of it. But most of our targets don't actually erase their computers. So if what we're looking for they can see, they'll remove it. So I've concentrated on looking for things that they don't see. Now this is a picture up here from some of collaborators of mine, Nasser Merman, he's at NYU Poly. And what's really interesting about that image is that's the middle of a JPEG. So JPEG digital images, the beginning has a header and a color map and EXIF information. And then there's the Huffman and compressed region, and then there's a footer. And what they did was they actually removed the beginning of the file. They removed the end of the file. And just from the data in the Huffman compressed region, it's possible to reconstruct a visible picture. And that was done in 2009. And still today, most people think that's not possible. We recently did some work in collaboration with CMU. We can take the second half of a gzip file, throw away the first half, and we can reconstruct the data in the second half. And that's really hard because it's an adaptive compression algorithm, but it's possible with a combination of trial decompressions and reassembling the table and then doing a linguistic model to actually recover the data. So it's really interesting. It's like a big puzzle. And then the last one is large amounts of data is essential. So most computer search techniques, they fail when the amount of data you have gets bigger and bigger and bigger. Because if you have a certain false positive rate, if you increase the amount of data you have by a factor of 10, you increase your false positives by a factor of 10. I'm trying to develop techniques that actually work better the more data you throw them at. So here's an example from a paper we did a few years ago, I guess 2 years ago now. We looked at all the hard drives in our corpus, and we have about 2,000 hard drives when this was done. And we can recognize IP packets that are in the swap files and in the hibernation files. And every IP packet has a MAC address, and every access to two MAC addresses, the machine that it's on and the router or the switch that it was going to. And so by scanning all these machines, we're actually able to reconstruct the physical networks that some of the drives belong to. The yellow boxes are hard drives, and the blue boxes are MAC addresses that were in IP packets that were on those hard drives. And then, lo and behold, we graph it all, and we get networks that correspond to where these hard drives were purchased. And that big circular network corresponds to a collection of computers that were bought in India. And then the top diamond, those are two computers that were in a service shop in Israel. And actually, one of the computers came from the West Bank, and one of the computers came from Israel. But they were both put onto the same network. And so we were able to pick that up. So this is a really powerful technique. If you have a very large collection of hard drives, you can actually find who was talking to the same wireless router by virtue of this residual data that was left behind. So in this talk, I'm going to talk a little bit about some digital forensic challenges. I introduced my group and talk a little bit more about digital forensics. I'm going to talk now about the big challenges facing digital forensics. And then I'm going to talk about this big innovation that we've been working on literally for 8 years, which is just about to put into a tool that will be usable by a number of law enforcement organizations. And if you have questions at this point, I could take one or two. Any questions? No? Yes, ma'am?
You mentioned that you bought some of the computers off of eBay.
Yes.
I remember some years ago when I was teaching, I had Sync magazine, and I think they went and bought 60 computers randomly off of eBay, but they were able through forensics to determine people. They could have easily stolen people's identities.
Yes.
It was horrifying.
It is horrifying.
They called them students, lawyers, every housewife, everybody, and they called them up, and you hear people screaming and dropping their phones. So I was just wondering.
It is appalling how much personal information is available on the secondhand market. My PhD thesis, I actually contacted people. I had IRB approval. We no longer contact people because it is too damaging to call people up. So we protect the information. We use it in a research context. We treat it as human subject information. And we have special approval from the MPS IRB to work with human subject data without the permission of the subjects. But it is interesting to note that legally they've given up all their privacy rights. There's actually a Supreme Court ruling on this. You throw something out, you've given up your privacy rights. The problem we have as privacy practitioners is that people don't know what they're throwing out. So for me as a researcher, I'm trying really hard to eliminate the resource data that I'm using in my research. I need it in my research, and I'm helping national security, but I would much rather that we didn't have this problem. So traditional computer forensics, we get a hard drive, we extract the data, we store it on a disk array, and we put the original data in an evidence locker. And we use things called write blockers so that we don't accidentally overwrite the data. Now these things actually are not perfect, but you can get them for USB sticks, you can get them for hard drives, you can even get them for cell phones. This is a device called a UFED, and it will take the data off of the cell phone. And there's a number of problems with this technology, but it basically works. And then this is an example of a computer forensics tool that a forensic examiner would have. It allows you to view all the files, the deleted files, the undeleted files, all the email messages, and do string searches through it. And it's basically like Windows Explorer for deleted data. Now, the problems that we have is not getting the data out. We have a little bit of that data. We have a much bigger problem, much bigger set of problems. And I have 5 key challenges, although I think I actually have 6. The first one is diversity. So our charter is to analyze any piece of information that might be found in any criminal investigation on any computer system on the planet. So this means we have to be able to understand every single file format. We have to be able to understand every piece of equipment that's currently in use or has ever been in use, every application, every protocol. And that's just not possible. So our second problem is not just that diversity, but that the data that we get may be inconsistent or incomplete. We may only get half of the file. We may get file that's been intentionally overwritten, maybe completely, maybe not completely. Much of the data that we're looking at has no public specification. So we need strategies for dealing with this. And until now, most computer forensics people have painstakingly reverse engineered file formats. And the problem with that is that there are more people developing new file formats than reverse engineering the old ones. And you never catch up. So computer forensics tools never work with the current data. The second problem we have is data scale. So if you go back over the years, every single computer forensics conference says that the biggest problem they have is dealing with the amount of data. Now, why is this never going away? It's because somebody goes out and they buy a 2 terabyte hard drive for $130. They have 10 of them in their office, and then they commit a crime, and the police have to show up and look at it all. Because, Lord help us, that there's one hard drive in that collection that we didn't look at that actually has the evidence of the crime. So we have to analyze the top-of-the-line computers that are being sold today. And the only thing we can analyze that with is the top-of-the-line computers being sold today. Moore's law never helps us catch up. Every other area of scientific investigation, the amount of computer power will eventually be enough to deal with the phenomena being studied. But that's not the case in computer science. We will never catch up. And a related problem is that the big data solutions in the other fields just aren't helping us out. They have much bigger budgets per byte. At CERN, they're making 1.5 petabytes of data a month. And that's roughly the same amount of data that the FBI lab is getting in a year. But they've got a lot more money at CERN than the FBI lab has. It's kind of surprising. They have, I think, 100 times more money. Also, the data that the physicists are getting is much more consistent than the data that we're getting in digital forensics. So this is a problem. Another problem is temporal diversity. As I mentioned before, we have to deal with every version going back to the past, because people are still using computers from the 90s. And if the criminal element knows that old computers can't be analyzed by the new tools, they'll just use the old computers, because they'd like to have systems that avoid analysis. We have this human capital problem I mentioned before. I can't hire enough people. Well, most of the people doing digital forensics, most of the practitioners are law enforcement. They have no background in computer science or information science. They are deadline driven. They're overworked. So we're seeing that it takes about 2 years to train one of these people up, and they don't hang around. It's really hard. The problem is worse on the developer side. In the past few years, I've had to learn about Unicode and mobile code and cloud computing and multiple operating systems and encryption and networking, because I have to know it all. And my students have to be able to know it all. And it's really hard to find people who care enough to learn all of this stuff. And it's really hard to put it into a framework where human beings can deal with this. It makes it really hard for us to find qualified developers. And our developers must be generalists. If we want to work with machine learning, we've tried hiring machine learning people. And I had one machine learning person. He spent 6 months dealing with the Unicode problem, because he was used to dealing with clean Unicode. And our data is anything but clean. Then we have this problem, the CSI effect. On television, everything works perfectly. Every investigator knows how to use every tool. Tools never crash. In the real world, it doesn't work like that. Tools crash all the time. Our tools look just like Windows Explorer. That makes people think that our tools are as easy to use and as easy to write as Windows Explorer. When we get encrypted data, we really have no choice but to try a brute force attempt to find all the passwords. We don't have magic technology to decrypt. When we find data that's been overwritten, we move on. We don't have technology that can recover data after it's been overwritten. That's just not possible. I know, there's this article out there that says you have to overwrite 7 times or 35 times. It's not true. 1 time of overwriting and the data cannot be recovered. So I mentioned that I had a company that failed. Well, it turns out that these tools are very expensive to develop. There's a very limited market. And my personal experience is that it's very hard to stay in business. So really, the government-developed tools tend to stay around longer. What are we doing about this all? This is the introduction to the research. So the current approaches that are being used simply don't scale. We spend years, we have weeks to analyze information that other people spend years putting together. We have weeks to reverse engineer file formats that other people spend years on. So we have to develop new kinds of algorithms. Algorithms that can automatically find the good stuff, algorithms that scale, algorithms that don't have to be calibrated, and algorithms that don't have false positives. And that's that's where I'm working. So now I'm going to talk to you about what we have to answer that. This is a technique of doing high-speed forensic analysis. It uses random sampling. So back in 2001, I was talking to a DARPA program manager. He said, can you give me something for the battlefield that will analyze what we would now call a terabyte hard drive in 5 minutes? And I said, there's no way you can do that. There's just no way you can analyze a terabyte hard drive in 5 minutes, because it takes 208 minutes to copy all the data off the hard drive. And if people know how you're going to analyze it, they will hide their data so that your analytical technique will miss it. Now, it turns out that there's one kind of search that you cannot hide from, and that's a random search. You can only be lucky or unlucky. So that terabyte hard drive, in 5 minutes, we can read 36 gigabytes, or we can do 90,000 seeks. And that's it. That's what you got to work with. So we could do random sampling. We use random sampling to predict the next president of the United States. We know the challenge is understanding who are the likely voters and who are they going to vote. How are they going to vote? Because we can't look into the future and actually do the random sampling. And so it's a lot of art. They're actually picking the sample and tuning it and so forth. We don't have that problem on the hard drive. We can actually perfectly pick a random sample on the hard drive. We can just pick a million randomly chosen sectors. What we can't do easily is identify the things that we've looked at. And the problem is we might end up in the middle of data when we're doing that random sampling. So human beings, like people in this room, we think of computers as devices that have files. There's a whole bunch of files. Like there's this another file and has a modified date and has a size and files and dates and sizes. But if you think about what's going on inside the computer, there's resident data, there's deleted data, there are sectors that might have no data, and they're all on the hard drive. So there's these blocks of sectors. We'll call them the white sectors. They have files that map to the root directory. They're in the tree somehow. And then there are these deleted data. And these are still sectors that have data in them, but you can't find them by exploring from the root directory. And then there are like these blank sectors. And they're blank, and they also can't be reached from the root directory. So if we do random sampling, we can't tell the difference between the sectors that can be reached from the root directory and the sectors that can't, because we'd have to map out the whole hard drive in advance, and we don't have the time. But we can look at a sector and tell whether it has data in it or whether it's all zeroed. That's good. That's good. So if we could look at the data and tell, well, is this an HTML file? Is this a blank sector? Is this video? Is it encrypted? Is it not encrypted? We could probably come up with a proportion of the number of sectors of each type. And we could come up with an inventory of the hard drive very quickly. So I'm going to do what we've all been taught to do. I'm going to simplify the problem a bit. And I'm just going to say, can we do random sampling to tell if the hard drive has been properly sanitized or not? A lot of organizations throw out hard drives, and I've actually called up organizations, and they said, well, we thought it was sanitized, but it turned out it wasn't. And when I buy hard drives on eBay, or when I used to, I'd find some drives, the first half of them was sanitized, and then maybe the power failed, or maybe a person got bored, and the second half had data. So what you could do is you could just randomly pick sectors. If we have that terabyte hard drive and we pick 10,000 sectors and they're all null, then the chances are probably the entire hard drive is null. So that's good. That's good. But we're not going to be able to do random sampling until if it's completely null. There might be one sector out of those 2 billion sectors that actually has data in it, and we're not going to find it with random sampling. So we can't say that the drive is wiped. We can only give statistics on the proportion of the drive that is wiped and the likelihood that we haven't missed it in our random sampling. So what about other distributions? Well, if half the drive is wiped and we do random sampling, then chances are half the sectors that we read are going to be wiped. But what if we read 10,000 sectors and those are the only 10,000 sectors that are actually the wiped ones? Well, then what happened was somebody actually knew which sectors we were going to pick in advance. They hacked our random number generator. That's really bad. That's why you have to use random numbers. They have to really be random. OK, so if you took statistics, this is called the urn problem. We have an urn with jelly beans in it, and some of them have one color and some of them have another color. And we're taking out jelly beans, and maybe the ones with the data are red, and the ones that don't have the data are green. And every time we take out a jelly bean, we can calculate the odds that we're going to miss the data. So we assume that that terabyte hard drive has 10 megabytes of data. That's 20,000 sectors. So the vast majority of them don't have data. Every time we pick one, we have roughly a 0.99999 chance of missing the data, which is really bad, right? We're never going to find it. But well, that's a number very close to 1. If we keep multiplying that number, if we keep repeating this every time, we have a very chance close to 1 of missing it. But if we keep multiplying together, those odds will drive down. So if we take 2 jelly beans, that's 0.9998 chance of missing it. But if we take thousands or tens of thousands or hundreds of thousands, the numbers come down really fast. If we take 500,000 jelly beans, then we have less than a 1% chance of missing the data on every trial. And this here is looking at the amount of data. If the amount of data increases, then you actually have also a lower chance of missing all the data. So if you work out the numbers, If you're going to pick up 500,000 random sectors and you're looking for 10 megabytes of data, you have a 99.3% chance of finding that data at least once. So good. We can do random sampling. We can do like 500,000 or 300,000 or however many. We can actually calculate the odds of missing the data, and we can print a certificate saying that there's a 99% chance that this drive has less than 5 megabytes of data on it. So in practice, we do a slightly better job. We use 64K sectors, blocks, instead of 512-byte blocks, because it actually takes the same amount of time to read a 64K chunk as to read a 512-byte chunk. But the statistics are much harder to understand, so I'm not going to go into them here. And then if we find interesting data, we might explore that local region. And we can update these results in real time, and we can have a nice GUI-driven application, and that's currently under development. We use this technique. Yes?
What is interesting data? So when we find interesting data, is anything non-blank interesting?
Well, keep that thought. Keep that thought. So certainly if we had a way of identifying what that sector was, other than being not blank, then we would have a way of classifying it. So that's something we call the classification problem, the file fragment classification problem. It's been a very important part of my research for the past few years. So we actually did this 2 or 3 years ago. We constructed we took an Apple iPod, and we put data on the iPod. And you can actually put images on the iPod. You can put a TrueCrypt volume on the iPod. You can put music on the iPod, because you can mount it. And the scenario is maybe there's this a person at your company, and they seem to be looking at a lot of stuff, but they have an iPod, and they want to take it out. And you want to look at all the data on their iPod. Well, so the challenge is, in fact, to identify the type of the file from its fragment. And here's a picture of the JPEG. We can recognize the header and the footer very easily. But the middle section is this Huffman-coded data area. How would we recognize that? Well, if you look at a sector of Huffman-coded data, you'll see that it looks like high entropy data. But it has this weird characteristic, which I didn't highlight. But apparently, whenever you have an FF, like here, if it has to be followed by a 0, 0. And that's because the JPEG internal coding uses FF not followed by a 0, 0 to denote the end of a section. So it has to escape, or they call it stuffing, the FFs with 0, 0s. So we can actually write a recognizer that looks for high entropy data, but with a disproportionate number of FF followed by 0, 0. And I have that coder here, and we have a small image. It's 31K. And these regions here are the ones that trip my coder looking for high entropy data, but with too many FF00 bigrams. And what's interesting is as you look at bigger and bigger JPEGs, this one has 57K of data, and this one has 2.1 megabytes of data, the amount of regions that trip that coder increase and increase. So if we have big JPEGs, we can actually recognize the Huffman-coded data very reliably without looking for the beginning and the end of the JPEG. We have previous research that tells us that most data on the hard drives is not fragmented, that most of the files are not fragmented. So if we find that we're in a JPEG, we could actually scan to the beginning and the end, and we could recover the entire JPEG. So we can find JPEGs with random sampling, which is pretty neat. Well, we can find other things with random sampling. HTML has these characteristic HTML tags. Mpeg, so you'd say, oh, well, we're just going to do this all with support vector machines, and we're going to look at bigrams and trigrams, and we're going to do machine learning, and there's some papers on that. But some of this stuff doesn't work well for machine learning. Mpeg files, the video files, it turns out they have frames, but every frame has a frame header, and it also has the number of bytes that are in that frame. So you can look at a region of the disk, and you can say, well, does this have anything that looks like a frame header? And does it point to something else that looks like a frame header? And that allows you to thread together the frames. And you can recognize Mpeg files with very, very high accuracy in this way. Because they have frame headers that all align, whereas random data doesn't. So even with these high entropy data formats, we can actually recognize a lot about them. We have a technique for finding Huffman-coded data that's based on autocorrelation. It turns out if you do autocorrelation on Huffman-coded data, you take all the data and then you move it over by a byte, and then you run a mathematical function on those 2 blocks, the statistics will change. And if you do that on random or encrypted data, the statistics don't change. Because if they did change, then that would be a way of doing cryptanalysis. And all the encryption algorithms are defended against the cryptanalysis. So we can actually distinguish random or encrypted data from Huffman-coded data, which is pretty cool. And then there's this idea of distinct data, which I'm going to go into in a bit later. But basically, if you have a JPEG, it turns out that every block of that JPEG is distinct. I want to say unique, but I'm not going to say unique because unique has this funny meaning that it's nowhere else in the world. It's distinct, meaning that whenever you find that sector, it is almost invariably a copy of the JPEG that it came from. The statistics are such that it's high entropy data. It's very unlikely that it would be come from another image or arise by chance. So we did this paper back in 2010. We combined the random sampling and the sector ID, and we could actually compute the forensic inventory, the forensic contents of the storage device. And the numbers that we got were actually very similar to the numbers that iTunes reported. So we were able to predict or to determine the size of the true crypt volume. We were able to determine the amount of the JPEGs and the amount of the free space. And our numbers actually matched the numbers that were on the iPod. And that's really cool because the Apple bought really cheap, really slow hard drives for these. It takes 3 hours to copy all the data off. But we were able to get accurate statistics with 2 minutes of random sampling. So that's the status as of 2010. But now we're going to talk about this thing here. This is the magic. So every sector of every JPEG is distinct, except for the sectors that those JPEGs have in common with other JPEGs. And every sector of every executable is distinct, except for the sectors that they have in common with others. And so the idea is you compute the cryptographic checksum, and we're using MD5 because it's fast and we're actually not worried about attacks because nobody's going to try to make their data look like our data. So you take every piece of video that you care about, every piece of child porn, every image that you care about, every piece of malware that you care about, and you hash them on 512-byte boundaries. And that's a hash database of blocks. And then you hash every sector of your hard drive or your optical disk. And those are on sector hashes. And the interesting thing about today's file systems is that files are aligned on sector boundaries. So the hashes match. So all you need is a big database of every sector hash of every file that you care about. And then you just hash randomly chosen sectors and you look them up in the database. It's pretty simple. Now that I've explained it, you could go off and implement it. There's no magic here. It's a neat idea. There are two things you need. You need to have distinct sectors, and you also need to have a database that has enough performance. So my student, Christina Foster, she just graduated, and this was her master's thesis. This is so cool. So we actually have 3 corpora where we know all the sector hashes, and they're freely releasable corpora. The first is GovDocs1. It's a set of about 1 million files that I downloaded from US government web servers. The second is OC malware, offensive computing malware. It's about 3 million samples of malware. And the third is NSRL, the National Software Reference Library. That's produced by NIST. We don't have the files. NIST has the files. They're all in a room about the size of this room. But I was able to get them to sector hash all the files. They have 12 million files, and the average file sizes. So NSRL is actually every piece of commercial software that's been sold in the United States over the past 30 years. And it's roughly 41 million files right now. It's 12.2 distinct files, 12.2 million distinct files. And it's not everything, but it's a lot. It's 11,000 software packages. And you can download all the file hashes from the NIST website. It's a great tool for computer forensics. So the first part of her thesis was she was looking at these 3 data sets and attempting to characterize whether they had distinct sectors or not. So we have this taxonomy. Singletons, that sector appears only once in the corpus. Pairs, it appears exactly twice. And then common, it appears more than twice. And you can ignore the secondary classification. So we looked at GovDocs, and we found, and these are downloaded from US government web servers, and we found that with a block size of 512 bytes, 98.93% were distinct of the sectors. Now, if we raise it to a block size of 4 kibibytes, we get 99.46% And the reason is, as you make the block size bigger, the common sectors tend to line up with sectors that are distinct, and they make the larger block completely distinct. And for a variety of reasons, it's better to work with 4K sectors than with 512-byte sectors. Same thing with the offensive computing malware, but here the numbers are lower. 88% are singletons. And with NSRL, they actually didn't do the 512 bytes, but at the 4 kilobyte size, 96% are distinct. Now, the interesting thing about the malware, well, I'll talk about that later if I have time. So this means that we can use distinct sectors to find known content. In fact, there are two ways we can do it. We can do the full media sampling. We can actually read every single sector of the entire hard drive, hash them all, and look for a single sector from our target files. And that will allow us to find the entire file. But if most of the file has been overwritten and one sector is left, we'll be able to find that one sector as long as it's distinct. So this means in that case of the child porn that I may have gotten, that was a hard drive and I couldn't recover any video from it. But if the known child porn that it came from was in some government database somewhere, and I had arranged with that organization to hash every one of their sectors, I could maybe find that there was a sector of child porn on that original disk. And I'm actually working now with the National Center for Missing and Exploited Children to go through their data sets and produce sector hashes rather than file hashes. And then the second thing you can do is you can do random sampling. If you have this high-performance database and you can look up these sectors and the sector hashes, you can do random sampling. And then if one of those sectors matches, remember before we were looking for 10 megabytes of data? Now we're just looking for one sector from a data set. We can find 10 megabytes of child porn as long as every sector of that child porn is in our database. Now, I mentioned before that I prefer to use 4K sectors instead of 512-byte sectors. Well, what do you do with these alignment problems, right? So maybe that my 4K sectors don't land on the same blocks as your 4K sectors because the hard drive has a logical block size of 512 bytes. So what we really do is we really read 8K sectors, and then we hash it on every 512-byte boundary. And so we avoid the alignment problem with this sliding window. That works pretty well. Now remember, we get 90,000 seeks in 5 minutes, and we can read 64K on each one of those seeks. Or we could read 36 gigabytes in one clip. We're not going to do that. So now we need to have a database that can actually service those requests, because we've got to be able to do 90,000 lookups. 90,000 lookups, and those are 64K. And so it's about 150,000 lookups per second. 150,000 transactions per second. Not for the random sampling, but for the full disk sampling. So my other collaborator, Joel Young, he's an assistant professor at NPS. He and I have been working on data structure. And what we've come up with is this data structure, which is basically a Bloom filter. And that sits in front of a B tree. And the whole thing can be compiled into this 72 gigabyte object. And you can put it on an SSD. And we can get about 150 transactions a second. 150,000 queries a second for a 128-bit hash to see if it's in the data set or not. And if it is in the data set, we get told the file number that it's in and the offset in the file. And this is some performance showing you how the different parameters deal. But the important thing to look at, and I can't reach up that high, is that we're able to do between 100,000 and 200,000 transactions a second sustained over time. And this shows you, this is a different thing. If you're on a laptop and the SSD is connected over a USB connection, you don't get as good performance, and it's not as consistent. So you really want an eSATA connection. But this is really cool, because this means that we can actually have a laptop with 8 gigabytes of RAM and then an external SSD, and we can deploy it into the field, and we can actually go to a border crossing and do random sampling in 5 minutes looking for child porn. Or we can go through the entire hard drive over the course of 208 minutes and look for one sector of child porn. So this is field deployable. We can look for known contraband. And this is a much more privacy-sensitive way to search than what Homeland Security is currently doing, which is opening up people's laptops at airports and double-clicking on my pictures. That's not really an intelligent way to do a search, and we've heard a bunch of horror stories. This is a nice systematic way to do a search, which pretty much removes the human element. If people are going to be searching for child porn, this is probably a good way to do it. But we can find a lot more than child porn. We can find encrypted PDFs. We can find encrypted files, encrypted Microsoft Word, provided that the data is not modified or copied or otherwise recoded. We need to have a database, and we can do searches on subject disks for stuff that's in our database. Any questions? Yes?
Okay, so now I'm just going to pretend one might have anything in front of any file that I actually am working on.
So it turns out it's remarkably difficult to prepend the file because most file containers will break if you do that. It's easy to append to the end, but you are correct. If you change the offset of the file, that makes this technique not work. Now, we actually do have another technique that slides a sliding window over every byte of the file. And that's work that we've been working on with Vasile Rousseff at University of New Orleans. And the problem is the searching is much slower.
In any case, you're relying on the fact that people don't know to wipe, to do a proper delete of their hard drive. So
People could just be using an encrypted file system where every file has its own encryption key. A lot of terrorist organizations operate by passing around encrypted files. So there's TTPs, standard procedures that they have. And they'll pass around the file to several people in the organization, and they'll exchange the decryption key out of band, maybe by phone. And this allows us to do triangulation on those data sets without actually being able to decrypt the files. And it may be they only have half of the file left, but we're still able to work it. This technique also works with network packets. So if the file was not moving over SSL, and you can get 512 bytes or 1024 bytes, you can now sector hash on every byte or use the TCP windows, and you can work this on network connections. This is the idea of doing sector hashing is the deep idea here, that if you sector hash, you can learn things about the subject media that before people were only able to learn with file hashing. So the first insight is having to use being able to use sector hashing, but then the requirement is being able to have a database that has 1 billion rows and 150,000 transactions per second. Yes, ma'am.
So you can identify where the JPEGs are, but you still need somebody to determine what the content.
That's correct. You need to have that data set, and somebody needs to have good provenance for that data set. So I can do blind correlations between 5 people's hard drives, and I may find that they were all a member of the carpool and they had emailed around the carpool schedule. But fortunately, we do have the National Center for Missing and Exploited Children. It's a federally chartered charity. They have a budget of about $50 million a year, and they have a big database of known child porn. And they actually know who all the victims are. And then we actually do have people who've broken the law, and we have files from their computers, and we know which of the files demonstrate criminal intent. So we do have those data sets. Now, what we could do is we could take 10 people who are known bad guys, and we could look for all the common sectors on those drives, and we could suppress out the sectors that are on drives of people who are not known bad guys, and then we could have the sectors that have known badness associated with them. And that's another paper that I could show you. So we know how to do that, and we actually have these statistical techniques that we can use for automatically finding the correlations that are present on the bad people's drives that are not present on the background drives.
So have you looked at doing something besides random seeks? I mean, given that there is structure to the file system.
So the danger is as soon as you start using the file system structure, then it gives the adversary a way to hide. So the question is, do you get enough advantage by using the structure that's there to overcome the disadvantage? And I haven't been able to demonstrate that to myself. That yes, you could look at the file names. Yes, but this works really well. And we have this advantage that you can't hide from a random search. Now, if you want to spend one of those 5 minutes doing something else, you're probably better off doing something that's very file system aware. And in fact, what you would do is you would download their ntuser.dat file. You would download the registry. You would download the list of installed programs. You would download the most recently used list of all the files. You would download the Windows preferences and the bookmarks on all the web browsers. If there's any SQL-like database associated with the web browser, you would download that.
I'm thinking that there's simpler, lower-level structure without needing to know it's Windows and version 7 or Mac OS or whatever, right? But there's simpler structure in terms of trees or simple graphs in the file system that you could potentially leverage to avoid sampling big regions of dead space.
Well, here's the problem. Let's say you did that, and let's say you could do it in 5 minutes, in 5 seconds, which you can't. So I can actually build file system structures.
Sure, but I could build an encrypted file system.
That's true.
You know,
That's true.
So that argument's not going to carry weight with
Well,
me in the sense that you're counting on the bad guy more or less using the system as was built.
so the problem that we have is that if you start doing that, what do you do with the regions that are not in file systems? Do you ignore them, or do you randomly sample them? Well, you have to randomly sample them, because otherwise that's an easy way to hide data. We have things like TrueCrypt, and a very common way of using TrueCrypt is to make a 64 megabyte TrueCrypt volume and put it at the end of a 5 megabyte video, and then append a video to the end of it. So it's a video file that will play, and the middle of it will appear to be corrupted because the middle of it happens to have a TrueCrypt container. As soon as you start paying attention to the data to bias your sampling, then you do open yourself up to particular kinds of attacks. At least with this technique, we would actually be able to detect that a large part of the drive is encrypted. So we can tell in 5 minutes not just whether or not it has the child porn on it, but we can give you the percentage of that hard drive that is encrypted. And that might be important too. If you have a drive where half of it's encrypted and it's a sketchy person, now the investigator can say, so why is half of your hard drive encrypted? I agree with you that biasing the sampling is a good thing to do, but I think that you want to bias the sampling based on the data that you read in the random sampling. So if I read the middle of a JPEG, it might be useful to go to the beginning, go to the end, and recover that whole JPEG. But the other thing that I mentioned at the beginning is that I don't have enough people. So if you have somebody who would like to work on this problem, we'd be happy to give them data and happy to give them software. And we'd even be happy to fund them because we really have more money than people. So where do we go from here? So digital forensics it's an important area. We have need for new algorithms, and we're just starting to develop an interesting algorithm here. We need to be able to adopt to different kinds of data. We need to be able to work with different resolutions of data, and we really need to be able to scale up to 10 petabytes, 40 petabytes. We need to have approaches that can automatically identify outliers and inconsistencies. So inconsistencies are a really important thing to look for because they indicate that something unusual is going on. One of the things that I mentioned earlier was that we saw lots of common sectors in the malware corpus. Well, it turns out that we've come up with a new way for identifying malware because a lot of malware authors take known malware that they have and they make small changes to it so that it will pass through the malware scanners. But they don't have the source code. So actually, many of the sectors are still preserved. And those common sectors on the malware corpus are actually indicative of malware. We don't see correlations between those sectors and sectors in the NSRL. We need to have ways for presenting this to those forensic investigators who don't have the background in computer science. So not only do we need good visualizations, we need good visualizations that people without a CS degree can understand. We need to be able to do this fusion between stored data, network data, and internet-based information. There's been a lot of stovepiping, but the investigators would very much like to be able to augment stored information with, say, Facebook searches, and do that in a manner that's that's legal. So different organizations have different requirements on what information they're allowed to look at and what information they're not allowed to look at. When I was in England, actually in Scotland, I was talking to some crime investigators there. And for them, it's much more interesting to go after Twitter, where everything is public, than to go after Facebook, because if they want to go after Facebook, they have to go through the embassy, because it's a US company, whereas Twitter, everything's public. So a lot of the techniques that we have here are just applicable to social network analysis or personal information management, data mining unstructured information. So there's a lot of opportunities here. And as I said, there's a lot of money available to do research. There's just more work to do than there are people to do it. So most of the forensic tools that are sold or distributed fail when they are deployed. And that is because people are not testing them on realistic data. So the data we have is really heterogeneous. We might have one hard drive with 10,000 email addresses and another with 2 million, and those are real numbers. The production environment is always more complicated than the test environments. And what we've seen is that the analysts that are using these tools have less experience and less time than the tool developers. So when the tools don't work in the field, the developers usually don't hear back. And they almost never can get the data that made the tool crash. So how do we deal with this? Well, we have to pay a lot of attention to usability and recoverability. I've become a person who does high-performance computing. I never expected to do that. We're trying to leverage open source. And we're trying to use programming languages that are safe and high performance. And of course, there are not that many. Like there's Python, which is very nice and safe and very slow. So we've been looking at C#, we've been looking at Java. And I've been coding in C++ and trying to code really, really safe stuff in C++. As you know, moving stuff from the lab to the field is itself a research problem. It's a research problem that is understudied. So in summary, there's this urgent need for fundamental research in computer forensics. Most of the work to date has only been looking at data recovery and reverse engineering. To solve tomorrow's problems, we need algorithms that scale. And working in this field is inherently interdisciplinary. And so we have active collaboration with many other schools. So any other questions? Yes?
Talk about making results understandable to non-computer science law enforcement. Do you foresee that it might be necessary to make them understandable to juries?
So I have actually testified in front of a jury on a computer forensics problem. And in my case, there were typos in the log file. I was testifying for the defense, and I was explaining that computers don't make typos, so the log files had probably been modified. On cross-examination, the expert for the prosecution said that, in fact, they had brought the log files into a word processor in order to print them. And the person was found, was acquitted. He didn't do it. He was framed. This is before I became a federal employee. I'm not allowed to testify for defense now. So in fact, making things understandable for juries sounds important. There's a big business of preparing visualizations for juries. Most cases that involve computer forensic data never get to the jury. The same was true of DNA, and it is the case now that most cases involving DNA never get to a jury. We do need to have ways of making things understandable for a jury, but because of the cost associated with a jury trial, most of the things that they will see will be produced in Photoshop, produced in PowerPoint, based on visualizations that a tool might have made. But no...
So you're talking the difference between automated and...
Right. So it may be that the expert for the defense and the expert for the prosecution will both run their tools and produce visualizations. They will pick and choose how they want to represent that, and they will show that to a jury. Many people in computer forensics, before they encounter the legal system, think, well, you're going to enter that hard drive into evidence? It's like, No, hard drives don't get entered into evidence. PDF files get entered into evidence. No jury is going to have a computer forensic tool running in the jury box. And no judge is going to be doing the investigation either. That's the job of the experts. Other questions? Yes?
I noticed you're down in Virginia. It's too bad you're not up here, because an acquaintance of mine just started a nonprofit, Hack Reduce, that they want to hack up big data. So they're going to have, like, I think 100 clusters or something, so have a chance, or else be one of the meetups that deal specifically.
Yeah, so
People who you will probably find people who are interested in a project like that.
So one of the things that we've done is we've created publicly available data sets at the digitalcorpora.org website. In here, I'll bring it up. So I finished it an hour, so now I can spend half an hour talking to anybody who wants to stay, which to me is really valuable. If we go to this website, see what we can do here. Oh, no, I don't have internet access. So anyway, if we could go to the Digital Corpora website, we would see that there are downloadable, freely available disk images, freely available network packet traces, freely available memory dumps. And what we've done is we've taken all this computer forensic data that is normally privacy sensitive, and we have created non-privacy sensitive analogs.
What's the website again?
Digitalcorpora.org. And so actually, I don't have any of the non-privacy sensitive stuff here. But so we won't show the privacy sensitive stuff. There we go. Sorry. Let's go back to play. There we go. So at digitalcorpora.org, we have scenarios that we have built with students playing the role of personas. And we have one case that involves a harassment against a university professor. And we have another case that involves a fictional terrorist group that is planning an attack on the National Gallery. And they don't want to kill people, they want to deface the art. And we ran that scenario over the summer. It involved people coming from out of the country, going to the airport, meeting up. And there was an insider at the National Gallery who was also trying to steal art at the same time that the attack was going to happen. And what we do for these scenarios is that we have the machines and we image them every day. We capture the network packets. Maybe we grab the memory. We have telephone images. We have laptop images. And then we make it all freely available on our website. And the purpose of that is so that researchers, so students, can actually build tools and work with realistic data without having to have IRB approval, because we don't think that it's ethical to give real privacy-sensitive data to students to do class assignments with. And we also don't think that if we can do the research with fake data, we think that we should be doing the research with fake data. So in many cases, we'll do research and publish papers based on our constructed data sets, but then we can do validation with our real data sets and know that the numbers work out. So any other questions?
Thanks, Simson.
Well, thank you very much.